Hello guys, my name is IBM and I'm still recording the past paper questions for gravitational fields. This is Physics 9702 paper 4, and if you want the document, find the link in the video description. The document is entirely free. And for those who have subscribed to membership, you can obtain the typed solutions in the document. The link is in the group for those who have joined the membership, and you'll find the clearly typed solutions in the group. The link to the clear typed solutions in the group with the clear illustrations, with the clear explanations as shown here in this document here. This is the same document that you'll find in my Google Classroom. Sorry, not in my Google Classroom, in my Google Drive. So let's go to part 9. In part 8, we stopped on question 25. In part 9, I want to start from question 26. By reference, the definition of gravitational potential. Remember, gravitational potential is the work done per unit mass in moving a test charge from infinity to a point in the gravitational field, and gravitational potential at infinity is defined to be zero. Explain why gravitational potential is a negative quantity. So this question you will always have many times, and the solution is always the same one. We have already said gravitational potential at infinity is defined to be zero. Gravitational potential at infinity is defined to be zero. We also know that the force or the gravitational force is always attractive. The gravitational force is always attractive. So it means that work is done or work is got out of an object when you move it from infinity closer to another mass. So work is got out. Work is got out of the object as it moves from infinity thus potential is less than zero, hence negative. But when you take an object to infinity, you must add energy to it. But remember, at infinity, energy is zero. So it means that when you are adding energy to the object, you are actually going through negative values. So bringing masses close to each other, work is done by the masses. In other words, energy is got or work is got out of the masses. In taking them further apart against the force of attraction, energy is added to them to overcome the force of attraction. So work is done on the masses. Whenever work is done on the masses, they gain energy. So gravitational potential increases. Whenever work is done by the masses, they lose energy. So the gravitational potential energy decreases. And yet at infinity, it is zero. So we are always moving through negative values of gravitational potential energy. Two stars, A and B, have their surfaces separated by a distance of 1.4 times 10 to the power of 12 meters, as illustrated in the figure. Point P lies on the line joining the centers of the two stars. The distance x of point P from the surface of star A may be varied, so x may be varied. The variation with distance x of the gravitational potential phi at point P is shown. So we see that the gravitational potential increases as we move far away from star A, and then it decreases as we move closer to star B. A rocket of mass 180 kilograms moves along the line joining the centers of the two stars from star A towards star B. So the rocket is moving from star A, moves along the line joining the centers. So rocket is moving along this line here and it is moving from star A towards star B. Use data from the figure to calculate the change in kinetic energy of the rock when it moves from the point where x is 0.1 times 10 to the power of 12 to the point where x is 1.2 times 10 to the power of 12 meters. State whether this change is an increase or a decrease. Okay, so let's look at these points. 0.1, I think 0.1 is this one here, where the potential is -10. This is 0.1. Then 1.2. 1.2 is this one here. 1.2 is that one there. So by conservation of energy, the change in kinetic energy should be equal to the change in potential energy if energy is to be conserved. So the change in kinetic energy should be the same as the change in potential energy if energy is to be conserved. And that means the change in kinetic energy, which is the same as change in potential energy, is going to be equal to the mass times the change in potential, because for potential energy we will get the mass times change in potential. And what is the change in potential between these? The mass, of course, is 180. The change in potential changes from, this is -10, and what is the potential here? -14 and -10. So the highest is -10, so potential changes from -10 to -14. So the change in potential is going to be -10 minus -14, then times 10 to the power of 8, which is equal to, so you have 14, of course that is 180 times 4 exponent 8. So this is 7.2 times 10 to the power of 10 joules. Now the question is it an increase or decrease? So potential, we notice that potential decreases because -10 is higher and -14 is a smaller value. So it means potential decreases from -10 exponent 8 to -14, which means that there is an overall decrease in gravitational potential energy. So potential decreases, so the change in potential energy is a decrease. There's an overall decrease in gravitational potential energy. That is the minus here. The negative would indicate a decrease, but I don't need to add it here. But in overall, the initial potential is higher than the final potential, which means that in overall there is an overall decrease in gravitational potential energy, or the change in gravitational potential energy is a decrease. And by conservation of energy, if potential energy decreases, it means kinetic energy should increase. Therefore, the change in kinetic energy is an increase. I want to repeat this. Potential decreases from -10 to negative 14. That is a decrease because negative 10 is bigger than negative 14, which means that on overall, the change in gravitational potential energy is a decrease. And if energy is to be conserved, if potential energy decreases, then kinetic energy should be increasing. Therefore, the change in kinetic energy is an increase on overall. At a point x equals to 0.1 times 10 to the power of 12 meters, the speed of the rock is v. Determine the minimum speed v such that the rock reaches the point where x is 1.2 times 10 to the power of 12 meters. Minimum speed. So at point x equals to 0.1, the speed is v. Determine the minimum speed v such that the rock reaches the point where x is 1.2 times 10 to the power of times 10 to the power of minus 10 to the power of 12 meters. Okay. So one, we notice that the maximum potential from the graph is, what is the maximum potential? I think the maximum potential is this one here, which is negative 4.4. So the maximum potential from the graph is negative 4.4 times 10 to the power of 8 joules per kilogram. And the initial potential is negative 10. So that means the change from the initial change in kinetic energy should be equal to the initial change in potential energy. So maximum potential from the graph is negative 4.4 times 10 to the power of 8 joules per kilogram. And that means the initial change in potential is going to be equal to negative initial change in potential is going to be equal to, of course, this will be negative 4.4 minus negative 10 times 10 to the power of 8, which gives us 5.6 times 10 to the power of 8 joules per kilogram. That's the initial change in potential. So, of course, initial change to reach its maximum, when here kinetic energy, because the potential increases, the kinetic energy first decreases up to this point here, and then now the kinetic energy increases. And by conservation of energy, it means that the initial change in kinetic energy should be equal to the initial change in potential energy. So the initial change in kinetic energy is the same as the initial change in potential energy by conservation of energy. So initial change in kinetic energy is a half mv squared. Of course, at maximum potential, the kinetic energy should be going to 0. So half mv squared is going to be equal to mass times change in potential, which means that v equals the square root of 2 times change in potential, because m cancels out. And this gives us square root of 2 times 5.6 times 10 to the power of 8. So this gives us square root of 2 times 5.6 exponent 8. Sorry, root of 2 times 5.6 exponent 8. Um, 2 times 5.6 exponent 8, which is 3.35 times 10 to the power of, that is 4. So the minimum speed here is going to be 3.35 times 10 to the power of 4. Now, the question you should ask yourself, why is this the minimum speed? Yet we have considered just the section where the potential increases from -10 to -4 to maximum value. So from the graph, the initial change in potential energy is an increase because the maximum potential energy is minus 4.5, and the initial potential is minus 10. So the initial change in potential is an increase, which means the initial change in kinetic energy is actually a decrease. Potential energy increases from x equals to 0.1 to x equals to around, I think it's around 0.5. I don't think it's 0.6. It's around here, the center around here, 0.5. So the initial potential energy increases from x equals 0.1 to around 0.5. So the kinetic energy decreases to a minimum value at about x equals to 0.5 times 10 to the power of 12 meters. Before now, it again starts to increase because after x equals 0.5, now we notice that the potential now decreases from negative 4.4 up to negative 14. So the kinetic energy decreases to a minimum value at about 0.5 before it again starts increasing until the rock reaches 1.2 times 10 to the power of 12 meters. So it means the minimum speed is attained at about x equals to 0.5 times 10 to the power of 12 meters. So minimum speed is attained at this point here, where the potential becomes maximum, or where the potential energy becomes maximum, because as potential energy increases, kinetic energy decreases. So the minimum speed is attained when at a point where x is 0.5, as shown there. So this value that we have obtained, considering the change in potential from -10 to -4.4, is actually the minimum speed. A binary star, binary means two, consists of two stars A and B that orbit one another, as shown. The stars are in circular orbits with the centers of both orbits at point P. A distance d from the center of star A. Explain why the centripetal force acting on both stars has the same magnitude. Why the centripetal force acting on both stars? These are binary stars orbiting one another. Now, what is providing this centripetal force? I think the gravitational force of star A provides centripetal force of star B, and the gravitational force of star B provides the centripetal force of star A. And by Newton's third law, the force of attraction between the stars are just equal but opposite. And if the force of attraction, which is the gravitational force, is just equal but opposite, it also means that the centripetal force on each of the stars are just equal but opposite, because the gravitational force caused by star A on star B is the one which provides centripetal force on star B. The gravitational force of star B, on star A caused by the gravitational force on star A caused by star B is the one which keeps star A in its orbit around star B. Therefore, it means the gravitational force of star B provides centripetal force on star A. By Newton's third law, the gravitational forces are equal but opposite, and the gravitational force between the two stars is given by the product of their masses and the square of their separation. Therefore, the centripetal forces are going to be equal. So precisely what I'm saying is that the centripetal force is provided by the gravitational force. The centripetal force is provided by gravitational force, but by Newton's third law. By Newton's third law, the gravitational force is the same but in opposite directions. Hence, it means centripetal force is the same. The gravitational force is the same but in opposite directions. Hence, centripetal force is the same. Hence, the centripetal force is the same. So, of course, the gravitational force is given by Newton's law of gravitation, which will be capital G, mass A, mass B, over their separation, which is 2.8 times 10 to the power of 8 kilometers, which becomes power 11 meters squared. And this is going to be the same for both of the stars, but just in opposite directions. The period of the orbit of the stars about P is 4 years. Calculate the angular speed omega of the stars. So of course omega is 2 pi divided by t, which is 2 pi divided by period is 4 years, so we change to seconds, so that is 4 times 365 days times 24 hours times 3600 to change to seconds. So you have 2 pi divided by 4 times 365 times 24 times 3600. So this is 4.98 times 10 to the power of -8 radians per second. Since they gave this to two significant figures, I'll round off this to 5.0 times 10 to the power of -8 radians per second. The separation of the centers of the star is 2.8 times 10 to the power of 8 kilometers. The mass of star A is ma, the mass of star B is mb. The ratio ma over mb is 3.0. Determine the distance d. So remember centripetal force. Centripetal force equals to m v squared over r. And of course, we know that v equals to omega times r. Since we have already omega here, it means that the centripetal force is going to be equal to m omega r squared over r, which becomes m omega squared r. So I'm going to use that equation for centripetal force. And we have said that by Newton's law, centripetal force of B due to the gravitational pull by A is equal but opposite to the centripetal force of A to the gravitational pull by B. That is by Newton's third law. The centripetal force of A, centripetal force of A caused by the gravitational pull by A, the centripetal force of B caused by the gravitational pull of A is equal but opposite to the centripetal force of A caused by the gravitational pull of B. Gravitational pull by B. So centripetal force of B, the centripetal force of B caused by the gravitational pull of A is going to be equal to mass mass of B times omega squared, then R for BR is this distance from the center. Of course, centripetal force is above the center. This distance is 2.8 times 10 to the power of 8 minus D above that center. So this is going to be 2.8 times 10 to the power of 8, then minus D, that is centripetal force of B. Then centripetal force of A will be mass of A times omega, because omega is the same, then times the distance from the center, which is D. Center of rotation is D. Then omega squared cancels out. And of course, we know that MA divided by MB is going to be equal to 2.8 times 10 to the power of 8 minus D divided by D. But remember, MA over MB is 3. So I have that 3.0 equals to 2.8 times 10 to the power of 8 minus D divided by D. So cross multiply 3D plus D, that is 4D, is going to be equal to 2.8 times 10 to the power of 8. So D is going to be equal to 2.8 times 10 to the power of 8 divided by 4. 2.8 exponent 8 divided by 4. That is 7.0 times 10 to the power of 7 kilometers. Okay, so I want people to just notice by Newton's third law, because the gravitational pull is the same, equal but opposite. So instead of equating the gravitational pulls, I just decided to equate the centripetal forces because they are just equal but also opposite. Because the centripetal force of B due to the gravitational pull caused by A is equal to the centripetal force of A due to the gravitational pull caused by B. So when you equate, but remember, centripetal force is the force towards the center, and the center of rotation is at P. So we always look for the distance of each of the masses from the center of rotation. Use your answers in A Roman 3 and B Roman 1 to determine the mass MB of star B. Explain your working. They said explain your working. So we said that gravitational force between A and B is equal to the centripetal force on A. Gravitational force between A and B is the one which provides centripetal force. So it is going to be the centripetal force is equal to the centripetal force on A about center P. That's my explanation. Remember, it is the gravitational force which provides the centripetal force. And the gravitational force between A and B is equal to G, the mass of A, the mass of B, divided by the separation of the two centers, which is 2.8 times 10 to the power of, now we're going to change this in kilograms, so I have to change this from kilometers to meters, so it's power 11 times 10 to the power of 11, then this is squared, that is gravitational force. It should be equal to the centripetal force on A about center, and centripetal force on A is going to be the mass of A, which is going to be capital M A omega squared, and then A from the center is the distance from the center is D. So when I combine these two, and of course MA cancels out, which means now I can find MB So MB is going to be equal to omega squared times D times 2.8 times 10 to the power of 11 squared divided by G. When I substitute, omega is, what's omega? 5.0 times 10 to the power of 5. 5.0 times 10 to the power of minus 8 squared times D, which is 7 times 10 to the power of 7 times 2.8 times 10 to the power of 11 squared. Divide this by G, which is 6.67 times 10 to the power of minus 11. Let me just press my calculator. That one times 5.0 exponent minus 8 squared, then times 2.8 exponent 11, 2.8 exponent 11, this is squared, divide by 6.67 exponent minus 11. So this is giving us 2.05 times 10 to the power of 26. I have to check this again. So 5 exponent minus 8. So this is squared times 7 exponent to the power of 10. Was this power 10 or power 7? This is in kilometers, so I have to change this to meters. It becomes 11. This is in kilometers, so I have to change it to 11. Yeah, those errors are always going to be there in an exam. So that is exponent 11 to change it to meters times 2.8 exponent 11 to change it also to meters, divide by 6.67 exponent minus 11. What have I done? 5 exponent minus 8 squared, 7 exponent 11, 2.8 exponent 11, but this is squared, 6.67 exponent minus 11. That is 2.05 or 06 times 10 to the power of 30. So 2.06 times 10 to the power of 30. So that is 2, or you can write 2.1 or 2.06 times 10 to the power of 30. Of course, if you had used omega as 2.98, you may end up getting here as 2.0 times 10 to the power of 30 kilograms, depending on how you round off, but this is still correct. A satellite of mass m has a circular orbit of radius r about a planet of mass M. It may be assumed that the planet and the satellite are uniform spheres that are isolated in space. Show that the linear speed v of the satellite is given by the expression v equals to square root of gm over r. G is the gravitational constant. Explain your working. Of course, when they say explain your working, we know that it's the gravitational force which provides centripetal force. So I'll just simply say gravitational force provides centripetal force. Okay, so if gravitational force provides centripetal force, gravitational force is capital G, capital M. Mass of the satellite is small m. Our radius of orbit is r, so that's r squared equals to centripetal force, which is mv squared over r. Of course, one m cancels, one r cancels. So gm over r equals to v squared. And this implies that v equals to the square root of gm over r. Two moons A and B have circular orbits about a planet as illustrated here. Moon A has an orbital radius of 1.3 exponent 8, linear speed VA and orbital period TA. Moon B has an orbital radius RB of 2.2 exponent 10 meters, linear speed VB and orbital period TB. Determine the ratio VA over VB. Okay, VA over VB. So we have already seen above here that V equals the square root of GM over R. So if I want VA divided by VB, this is for VA, it will be square root of G M over R for A. Then divide by the root of GM over R for B. Of course, GM cancels out and RB goes up, so it becomes square root of RB divided by RA, which is going to be the square root of RB is 2.2 times 10 to the power of 10. RA is 1.3 times 10 to the power of 8. So I'll just say 2.2 divided by 1.3 and the square root of the answer. That is 1.3. Let me check this. Oh, this is 8, sorry. 2.2 exponent 10. I was trying to avoid the power. 1.3 exponent 8. Then root of the answer. It's 13.00. 09. So that is approximately 13 to two significant figures, since they quoted the quantities to two significant figures. Then TA over TB. TA over TB, of course, T is the period. So we know earlier on that V is also given by omega times R, which is the same as 2 pi R over period. So what does that mean? So it means that VA should be equal to 2 pi RA divided by period of A. And at the same time for B, it means that VB should be equal to 2 pi R of B divided by the period of B. Now I'm going to combine those two equations. So VA over VB is the same as, I'm dividing the two equations. So that is 2 pi RA over TA. Then I will get the reciprocal TB over 2 pi RB. What does this simplify to? So 2 pi cancels. So it becomes RA over RB times TB over TA. So I want to make now TA over TB the subject. So making TA over TB the subject will be just swapping them. I'll take this one to the left and take this one to the right. So TA over TB is going to be equal to TA over TB is going to be equal to RA over RB, then times the reciprocal of this, which is going to be 1 over, or I just get 1 over VA over VB. I don't want to remove this because I already have this as 13. So TA so TA over TB is equal to that. So let's just substitute RA over RB. I think RA is 1.3, RB is 2.2. So that is 1.3 times 10 to the power of 8 over 2.2 times 10 to the power of 10, then times 1 over VA over VB was 13, 1 over 13. So this is going to be 1.3 exponent 8 divided by 2.2 exponent 8. Sorry, this was exponent 10. Divided by 13. So that is 0.0000454545, which is 4.545 times 10 to the power of negative 4. So this is 4.545 times 10 to the power of negative 4, which makes the answer to be 4.54. Let me just leave it 545 times 10 to the power of minus 4. Then the moon spins about its axis with angular speed of 1.7 times 10 to the power of negative 4 radians per second. Moon A is always above the same point on the planet's surface. Determine the orbital period TB of Moon B. So if Moon A is always at the same, is always above the same point on the planet's surface, let's first find the period of Moon A. So TA is equal to 2 pi over omega, since they gave us the angular speed. So this is 2 pi over 1.7 times 10 to the power of negative 4. 2 pi divided by 1.7 exponent negative 4. So that is 3.70 times 10 to the power of 4. That is the period. But also do not forget that the period of A divided by the period of B is equal to 4.545 times 10 to the power of minus 4 seconds. Sorry, that's a ratio. So what does that mean? It means that the period of B should be equal to the period of A divided by 4.545 times 10 to the power of minus 4, which is going to be 3.70 times 10 to the power of 4 divided by 4.545 times 10 to the power of minus 4. So from my calculator, this is 8.1 times 10 to the power of 7. 8.14 times 10 to the power of 7 seconds. 8.1 times 10 to the power of 7 seconds. Okay, so I want part 9 to stop there. See you in part 10. Bye bye.